Hello everyone, myself Rekha, working as an assistant professor in Department of Computer Science in PSG College of Arts and Science. The content of today's sessions, let's see about deadlock, the system model, deadlock characterizations, resource allocation graph, and the various methods for handling the deadlock, deadlock prevention, avoidance with three different modes, safe state, resource allocation graph, and Banker's algorithm and deadlock detection, and at last we'll see about a recovery from deadlock. Let us see about the main basic definition of deadlock. So deadlock may occur when two or more processes trying to get same multiple resources at same time. So here deadlock is a situation where set of processes are blocked because each process is holding the resource and waiting for another resource acquired by some other process. So say for example, when two trains are coming towards each other on same track and there is only one track, none of the train can move once they are in front of each other, right? So in the similar situation occur in the operating system also. So when there are two or more processes hold some resources and wait for other resources held by other process. So say for example in the below diagram, the process 1 is holding the resources 1 and waiting for the resource 2 which is acquired by the process 2, and the process 2 is waiting for resource 1. The system can be modeled as a collection of limited resources, so which can be partitioned into a different categories that are allocated to number of processes. So each resources may have a different needs. So here the resources are categorized into memory or printer or CPU, tape drives, open files. So all these resources within the category are equivalent, and the request of all the category can be equally satisfied by any one of the resources in that category. So if this is not the case, say for example, that means if there is some difference between the resources within a category, then that category needs to be further divided into a separate categories. Say for example, the printer. If you take a printer need to be separated into a inkjet printer or laser printer. So some categories may have a single resources. So here the process in the operating system, they use different resources, and all these resources have some following ways. So starting from the request, how the resources are requested, using of the resources, and at last ending to release all those resources. So in normal operation, a process must request a resource before using it and release it when it is done. So we have to follow some sequences. So initially we'll start with the request. If the request cannot be immediately granted, then the process must have to wait until the resources it need become available. For example, the system calls open function or memory allocation, new, and request. So all these functions are used for requesting the resources. Okay, and the second function is the use function. Here the process uses the resources. Say for example, the print to print, we need a printer or read from the files. So to use the function, the process use the several resources. So and the third thing is a release function. So here the process relinquishes the resources so that it becomes available for other process also. Here we will be using close function, free, delete, and release. In deadlock characterization, deadlock can arise if any one of the four conditions hold simultaneously. So the first one is the mutual exclusion. So here one or more than one resources are non-shareable. That means only one process can use at a time. For example, if the process 1 accessing the resource 1 means the other process cannot share it, and the second one will be the hold and wait. Here the process is holding at least one resources and waiting for the other resources. Example, so the process 1 is holding resource 1 means and requesting for the other resource 2, and the process 2 is holding resource 2 and it is requesting for the resource 1. And the third one is non-preemption. That means a resources cannot be taken from the process unless the process releases the resources. So once a process is holding a resource, that is, once its request has been granted, then that request or that resources cannot be taken away from that process. So until the process is voluntarily released. First condition is the circular wait. Here the circular wait is a set of processes or waiting for each other in the circular form. So out of the four condition, this circular wait is implies the hold and wait condition, but it is very easier to deal with the condition if the four condition are considered separately. Resource allocation graph. So in some cases, deadlock can be understood more clearly through the use of resource allocation graph, which have some following properties. So here a set of resources categories R1, R2, R3, so which are appear in a square nodes on the graph. So dot inside the resource nodes which indicate a specific instance of the resources. Example, two dots might represent two laser printer and a set of process which is denoted as a P1, P2, P3, and there are two different edges, request edge and assignment edge. Request edge means a set of directed arc from process to resources which indicates the process have requested the resources and it's currently waiting for that resource to become available. And when we move on to the assignment edge is a set of directed arc from resources to process. You can see the arc from resource to process, which indicate that resources has been allocated to the process, and that process is currently holding the resource R. So note that request edge can be converted into a assignment edge by reversing the direction of the arc when the request is granted. And we can also say, however, you have to note carefully that request edge is pointing to the category box. So whereas assignment edge is from a particular instance dot within the box. In resource allocation graph, we have to know the structure of each and every terminologies. The first one is a process. The process is represented as a circle. And the second one is a resource. So here we have the resources may have four instances. So that's why we just mentioned a four square, small square box within the large square. And the third one is the process which requests the instance of the resources. So that's why you can see the arc from process to resource. And the last one will be the process is holding the instance of a resources. So here you can see the arc from resources to the process. So here this is a good example for resource allocation graph. If the graph does not contain a cycle, that means if it contain no cycle, then the system is not deadlocked. Okay. So if the resource allocation graph it contains cycle means we can say some deadlock is exist. So each resource or categorized contain only one single instance. If the resources category which contain more than one instance, then the presence of a cycle in the resource allocation graph that indicates there is a possibilities of the deadlock. In this example, the process P1 is holding the instance of the resource type R2 and waiting for an instance of resource type R1. And the second process is holding the instance of a R1 and the instance of R2 and it's waiting for the instance of R3. That means resource 3. And the last one, the process 3 is holding the instance of the resource 3. In this graph, all the three process P1, P2, P3 are deadlocked. Why? Because the process 2 is waiting for the resource 3 and which is held by the process P3. and process P3 is waiting for either P1 or P2 to release the resource R2. So in addition, the P1 is waiting for the process 2 to release the resource R1. So all the process P1, P2, P3, all the three are deadlocked. Here the graph with a cycle but no deadlock. If a resource allocation graph does not have a cycle, then the system is not deadlocked. It's not in a deadlocked state. If there is a cycle, then the system may or may not be deadlocked. There are three ways or three methods for handling the deadlock. The first one is the deadlock detections. So deadlock can be detected by the resource scheduler. So they can keep track of all the resources that are allocated to different processes. So after a deadlock is detected, it can be handled using a given method. So when all the processes that are involved in the deadlock are terminated, so this approach is not useful for all the progress made by the process is destroyed. And the second method is resources can be preempted from some process and given to other until the deadlock situation is resolved. And the second one is the deadlock prevention. So it is very important to prevent the deadlock before it can occur. So to prevent a deadlock before it can be occur. So the system check each and every transaction before it is executed to make sure that it does not lead to a deadlock. If there is even a slight possibility that a transaction may lead to a deadlock, it never allowed to execute. And the last one is deadlock avoidance. So it is better to avoid a deadlock rather than taking a measure after the deadlock has occurred. So in deadlock avoidance, it avoid the deadlock by rather by measuring after the deadlock has been occurred. So avoidance is a kind of futuristic in nature. So by using this strategy, avoidance, we have to make an assumption. So we need to ensure that all the information about the resource which is processed and need to know able to we need to know prior to execution of the process. So we use a banker's algorithm in order to avoid the deadlock. So the methods for handling the deadlocks. So if a system does not employ either a deadlock prevention or deadlock avoidance algorithm, so here the deadlock situation can be arise. So the undetected deadlock will result in deterioration of the system's performance because the resources being held by the process that cannot run, and because more and more process as they make request for the resources will enter the deadlock state. Here the system will stop functioning and will need to be restarted manually. If in many systems, deadlock may occur infrequently. Here the system may have a mutual recovery method for such condition and may simply use these techniques for deadlock recovery. Prevention. So deadlock prevention means try to find a solution before deadlock occur. So deadlock can be prevented by preventing at least one of the four required conditions. So we have to try to remove all the four conditions or make false or try to make any one condition false. So here we have four different conditions: mutual exclusion, hold and wait, no preemption, and circular wait. uh, Mutual exclusion. To prevent the deadlock, first we have to make the mutual exclusion false. So how this is happen? So just we have to share the resources. Say for example, all the three processes are sharing the same resources, but here the printer is a non-shareable. So at a time only one process can be printed. The other has to wait. So this concept will not be work for all the case to make a mutual exclusion false. So to recover this, the shared resources like read-only files which do not lead to a deadlock. So unfortunately, some resources such as like a printer, a tape drive, they require a exclusive access by a single process. And the second condition is a hold and wait. Here we have to make the hold and wait as a false state. So this is possible by giving all the resources before its start. So to prevent this condition, the process must be prevented from holding one or more resources while simultaneously it's waiting for the other resources. So there are several possibility. In the first possibility, it require all the process request all resources at a single time. So this can be wasteful of system resources. So if a process needs one resource early in its execution and does not need some other resources until much later. And in the second possibility, it require the process is holding the resource must release them before requesting a new resources, and it may reoccur the released resources along with a new one in a single new request. So this can be a problem if the process has partially completed an operation using a resource, and then it may fail to get it reallocated after releasing it. So either of the method can be described above can lead to a starvation if a process require one or more popular resources. Condition is no preemption. So here also we have to make the condition false. So it means that it is the opposite term of preemption. So we have to make the preemption is true. So how can we make the preemption is true? Only by using a time quantum method. So say for example, so each process is allocated with a given time, or it may allocated with some time. So the process one allocated with time to access the resource. So whenever the time is over, the process should release the resources, and the other process is allocated with some other time to access the resources. So by using a preemption, we can prevent the deadlock. So preemption means is a process of allocation by making a condition of deadlock. So when it is possible, so there are two different approaches. So in the first approach, if a process is forced to wait when requesting a new resource, then all other resources previously held by the process are implicitly released. Okay, in the another approach, so when a resource is requested and not available, then the system look to see what other process or currently have those resources and are themselves blocked waiting for other resources. So if such process is found, then some of their resources may get preempted and added to the list of resources for which the process is waiting. So in no preemption, if the resources are either available or nor held by the waiting process, the requesting process must has to wait. While it is waiting, some of its resources may be preempted, but only if another process requests them. Last condition is circular wait. So we have to make the condition false. So this will prevent a deadlock. To remove the circular wait, just give the numbering to all the resources. Example, the CPU is 1, the printer is 4, so that the process can request resources in increasing order. By doing this, we can remove the circular wait. So say for example, we have to set a priority. F tape drive is equal to 1, disk drive is equal to 5, and F printer is equal to 12. If the process 1 want to use the tape drive and printer, it should first request the tape drive and then it goes to the printer. So we have to check and compare the priority of the tape drive is less than the printer. So by making finally by making all the four condition false, or try any one condition to false, we can prevent the deadlock. So one way to avoid the circular wait to number all the resources and to require that process request resources only in by increasing or decreasing order. In the other words, in order to request the resources, or a process must first release all the resources. So by checking the condition, so I is greater than or equal to j. So one big challenge in this scheme is determining that the relative ordering of different resources. In deadlock avoidance, so it is better to avoid rather than taking measure after the deadlock has been occurred. So avoidance is one kind of futuristic in nature. By using this strategy of avoidance, we have to make an assumption. We need to ensure that all the information about the resources which process will need or known to as a prior to the execution of the process. So we use Banker's algorithm in order to avoid a deadlock. Safe state in deadlock avoidance. When a process requests an available resources, system must decide if immediate allocation leave the system in a safe state. So here the system is in a safe state means if there exists a sequence of process 1, process 2 and all of the process in the system, such that for each process, that means Pi, the resource that Pi can still request can be satisfied by currently available resources by incrementing the process state. That is, if the process resources are not immediately available means, then the process has to wait until the other process have completed. When the process is completed, the process can obtain the needed resources and they can execute and return the allocated resources, and at last it can be terminate the resources. So when a process is terminated, it can be incremented by obtaining its needed resources. There are three basic facts. If a system is in a safe state, then it's considered as there is no deadlock. If the system is in unsafe state, there is a possibility of the deadlock, and avoidance, which ensure the system will never enter a unsafe state. In this pic, you can see there are two different states, safe state and unsafe state. When the deadlock is occur only on the unsafe state, not on the safe state. As long as the state is safe, operating system can avoid unsafe state. In unsafe state, the operating system cannot prevent the processes from requesting resources in such a way that a deadlock occur. So the behavior of the process controls the unsafe state. In avoidance algorithm, to avoid the deadlock, one may require additional information about how the resources are to be requested. For one instance of each resource type, the resource allocation graph algorithm is used. That means only one printer can be attached to the computer or scanner or one CPU. For avoidance of multiple instances of each resource type, we need to use a Banker's algorithm. That means more than one hard disk can be connected to the computer. So here, the single instance of a resource type, we need to use a resource allocation graph. For a multiple instance of resource type, we need to use a Banker's algorithm. So to avoid the deadlock, we need to perform two algorithm, that means two technique, one for resource allocation graph and the second one is Banker's algorithm. So the resource allocation graph is used for single instance of resource type and the Banker's algorithm is used for multiple instance of resource. In deadlock detection, after allocating the resources to the process, the operating system will check for the detection of deadlock or not. So in order to check the deadlock, we have two approaches. The first approach is the single instance of resource type. If all the resources in the graph contain a single instance means, we will use the corresponding wait for graph. And the second approach is multiple instance of resource type. If all the resources in the graph contain multiple instance, which means we will use similar to a Banker algorithm. So here we can detect the deadlock when there is a single instance of resource. If all resources have only a single instance, then we can define a deadlock detection algorithm as a resource allocation graph, which is called as wait for graph. To obtain this graph from the resource allocation graph by removing the resource nodes and collapsing the appropriate edges. This resource allocation graph. So here it specifies the P4 is waiting for R2 and R2 is allocated for P1. So here the P1 is waiting for R1, but R1 is allocated for P2. That means the process 2. Likewise, every process is allocated and waiting for some other resources. So we have to construct the wait for graph from resources allocation graph. So to construct this, simply we have to remove the resources and connect it to the process. So here the P4 is waiting for R2, but R2 is allocated to P1. So connect P4 and P1. That means the P4 is waiting for P1 to release the R2. Same way, P1 is waiting for R1. R1 is allocated to P2. So remove the resource 1. P1 connected to P2. That means P1 waiting for P2 to release the R1. In single instance of each resource type, a deadlock exists in the system if and only if the wait for graph contains a cycle. To detect the deadlock, the system needs to maintain the wait for graph and periodically invoke an algorithm that searches for a cycle in the graph. An algorithm to detect a cycle in a graph which require the order of n square operation, where n is the number of vertices in the graph. In several instances of resource type, an algorithm employs several time varying a data structure that are similar in the banker's algorithm. So in available, a vector of the length m indicates the number of available resources of each type. Allocation, an n cross m matrix defines the number of resources of each type currently allocated to the deadlock recovery. If the system contains deadlock, then with the help of recovery mechanism, we can recover from deadlock. So when deadlock is detected, how we can recover the deadlock? For this, there are two approaches. There are two options for breaking a deadlock. One is simply to abort one or more process to break the circular wait. The other is to preempt some resources from one or more of deadlocked process. In the first approach is process termination. So there are two sub-technique. The first one, aborting all the deadlocked process. That means out of 10 process, 3 process were deadlocked means we can abort all the 3 process. And the second sub-technique is aborting one process at a time until the deadlock cycle is terminated. So if 3 process was deadlocked means the first kill the first process and apply deadlock detection algorithm in order to know the deadlock cycle is eliminated or not. Suppose 100 process was deadlocked means abort one process at a time until the deadlock cycle is eliminated. So here it has too much of overhead because every time applying a deadlock detection algorithm after killing the process, so that this may can be a drawback of the main approach. Second approach is resource preemption. So here 3 issues need to be considered. The first one is selecting a victim. So that means here the process we have to select. Suppose 10 process are suffering from deadlock means from this the resources which is released low priority process and completed with less execution time. And the second one is rollback. This means a beginning. So we have to roll back to the beginning and start execution from the initial process. Approach is starvation. Here the process has to wait for long amount of time for execution. By considering all these 3 issues, resource preemption is done. So therefore the system recover from deadlock by process termination and resource preemption. Thank you very much for your patient listening. I hope that you all understand the concepts of deadlock. Thank you very much.